This lesson is diagonalizing the matrix. So this form and this form are the same. Again, this and this, they are the same. It's just written in different ways, okay? This is the matrix A. So here's matrix A. I recopy it. Subtract lambda I. In this situation, we have a 3 by 3 matrix. So therefore, your identity should also be 3 by 3. Okay, so if this was 4 by 4, identity should be 4 by 4, and so on. Now, when you multiply lambda to identity, only the diagonal will get the identity. So lambda times I is back to lambda. Everything else is just 0. After that, just subtract across or add. So A subtract lambda I. So just subtract across. That's it. 1, -1 subtract lambda is this. 4 subtract 0 is 4. -2 subtract 0 is -2. -3 subtract 0 is -3. 4 subtract lambda, which is here. 0 subtract 0 is just 0 right there. -3 subtract 0 is -3. 1 subtract 0 is 1. And then 3 subtract lambda is this. After that, take this matrix, then go get the determinant, okay? Take this matrix and then go get the determinant, all right? So determinant of A minus lambda. Here I'm going to use cofactor. Now, if you look at this matrix very carefully, we do have a 0 here. Use the 0 so that it makes things a little easier and faster, because 0 times anything is just 0. One more time. In your matrix, when you are looking for the determinant, if I have a 0 somewhere, use it, okay? So you can do any columns and any rows, okay? Again, when you do cofactor, you can do any columns and rows, all right? But when you see a 0, that makes it a little bit faster, so you don't have to do a lot of solvings, okay? So I'm going to use -2. Again, the first one is always a plus, always a plus. So -2, all right? So plus, as you can see, plus, minus, plus, okay? So -2, using this column and this row, all you have left is just this right here, just this part here. And then next, -0. So this column and this row go away. All you have left is these two and these two, which is here, okay? After minus, then plus, plus this one. So this column and this row go away. So you just have this part only, which is here, okay? After that, do your determinant for the 2 by 2. So A times D minus B times C. So -3 times 1 is this, minus -3 times 4 lambda, which is here, plus anything times 0 is just 0. Next, 3 minus lambda. So -1 lambda times 4 minus lambda, which is here, minus -3 times 4 gives me -12, but there's another negative, so become plus 12, okay? After that, do more multiplying and then simplify it down a little bit more. So here's -3. -3 is right here. Negative and -3 gives me +3. +3 times 4 gives me this 12. -3, negative and -3 will gives me +3. Minus this lambda gives me -3 lambda. 0 is just 0, so I'm just bringing it down. Now, since it is 0, I don't need to keep writing 0, but I purposely keep writing 0 so you can see where the 0 came from, okay? Next, right here, lambda minus lambda gives me lambda squared. -1 times negative lambda will be positive lambda. 4 subtract 4 times -3. 4 times negative lambda will give me -4 lambda plus the 1 lambda gives me this -3 lambda. And then -1 times 4 is -4. -4 plus 12 gives me +8. Okay. Next, Negative 3 plus 12 gives me 9. 9 times negative 2 gives me negative 18. And then negative 2 times this negative 3 lambda gives me 6 lambda. And then 0. All right, so 3 times lambda squared. 3 times negative 3, so negative 9 lambda. 3 times 8 gives me this positive 24. Lambda, negative lambda, and lambda squared gives me negative lambda cubed. Negative lambda times this negative 3 lambda gives me positive 3 lambda squared. Negative lambda times 8 gives me negative 8 lambda. Now combine like terms, put everything together. So here I only have 1 lambda cube, which is here, okay? So 3 lambda squared, 3 lambda squared, so 3 and 3 gives me this 6. Here I have 6 lambda minus 6 lambda minus 9 lambda gives me negative 3 lambda. Negative 3 lambda plus another negative 8 lambda gives me negative 11 lambda. And then negative 18 plus 24 gives me this positive 6. I'm going to take out the negative. So when I take out the negative, all of these sign will be changed. Again, when I take out the negative right here, when I take out that negative right here, all of these will be changed. So negative become positive, positive becomes negative, negative become positive, positive become negative. So this right here is our characterized polynomial. One more time, this right here is our characterized polynomial right there. So this is our polynomial. Now this is factorable. So I'm going to move this up here just a little bit. Okay, so this is factorable, but I'm going to use the rational root theorem, and I hope you remember the rational root theorem. So P is this 6, Q is this 1 right here. The factor of 6 is 1, 2, 3, 6. So all of the number of 6 is all of the number that multiply give me 6 will be 1, 2, 3, and 6. So all of the factors of 6 is 1, 2, 3, and 6. Again, all of the number that multiply that gives me 6 is 1, 2, 3, 6. All of the number that multiply will give me 1 is just 1. Now P divided by Q, 1 divided by 1 is this 1, 2 divided by 1 is 2, 3 divided by 1 is 3, 6 divided by 1 is 6. However, when you do rational root theorem, you have to add plus and minus in, so that because you don't know which one will be the solution. The positive could be the solution, the negative also could be the solutions. So you have to consider plus and minus because you don't know which one will be the solutions. Now I'm going to go this a little bit faster because we don't have enough time and there's not enough space to do all of this. So I'm just going to jump to the solution so it makes it a little bit faster. All of this right here is the possible solutions, but we don't know which one is the solutions. So, but for the sake of time and all the work, let's make this a little bit faster. So I'm going to use positive 1. Okay, by synthetic division. I hope you remember synthetic division. So I'm going to use positive 1. Write down the 1. The 1 is right here. Negative 6 is here. 11 is here. Negative 6 is here. So using synthetic division, only take the coefficient of each term. 1, negative 6, 11, and negative 6. That's what I have here. Okay, now I'm going to use the possible solution. So I'm going to start out as positive 1. So here's the positive 1. So in synthetic division, always bring the first one down. Bring the first one down. So 1 times 1 gives me 1. Bring up the 1 right here. One more time. When you do synthetic division, always bring down the first one. So 1 times 1 is 1. Negative 6, subtract negative 6 plus 1 gives me negative 5. 1 times negative 5 is negative 5. Bring the negative 5 up. 11 subtract 5 gives me 6. 1 times 6 is 6. Bring the 6 up. Negative 6 plus 6 gives me 0. When the last number is 0, then this is the solution. One more time. When the last number right here, the last number here is a 0, this is the solution. If this is not a 0, then you have to use the next one. One more time. When you do the synthetic division, this part right here, if it is a 0, then this is the solution. If this is not a 0, then you have to use another possible solution. You got to use one of these, okay, in this list. One more time. In synthetic division, this way here, if it's equal to 0, then 1 is the solution. If this is not 0, you have to do another number from the list, okay, from this list, okay. Now, since this is a solution, bring it down. However, when you bring it down, you have to do the opposite. So if this is plus, then this has to be a if this is a positive, then this has to be a negative. Always opposite when you bring it down. So if this is positive, so bring it down becomes minus. Next, I have 1, so 1 square, 1x squared, negative 5x, and then bring down the 6. Now I use x here is just to separate this lambda, okay? Again, I use this x here just to separate the lambda, all right? But again, it's still the same, all right? So whatever this is, if it's the solution, always opposite. So if this is positive, bring it down negative. 1, bring it down, so x squared, negative 5, bring it down, negative 5x. Positive 6, bring it down. Now this is factorable. X squared minus 5x plus 6 is factorable, and it comes out to be x minus 2, x minus 3. Now solve for it, so it will just become lambda 1, 2, and 3. Solve for it, so lambda is equal to 1, and lambda here, solve it, equal 2, solve it, that gives me 3. Again, I use the x, it's just to separate the lambda, but it's the same thing, okay? So once it is factorable, always opposite, so negative 1, solve for it, that becomes positive 1. Solve for it, becomes positive 2. Solve for it, that becomes positive 3. So these are the eigenvalues that we need to use so that I can get the basis for each of the eigenvalue. Again, this right here is the characteristic of the polynomial. This right here is the eigenvalue. Okay, again, this is the polynomial. This is the eigenvalue. Now use these eigenvalue to get the basis or vector. Okay, so here I have, so earlier I have 3, so 3. So instead of using lambda again, I put the 3 in. Again, a minus 3 lambda, where did I get that from? So here is the eigenvalue, 1, 2, 3, okay? And then I will use this part right here, a minus lambda I, to get the basis for each of the lambda, each of the eigenvalues. So the first eigenvalue would be 3. Instead of using lambda, I put the 3 in. So here is the original matrix A, 3 times I. Again, all of the diagonal will just have 3. Everything else is just 0. Just subtract across, subtract across, subtract across, and this is what I have. Now use this matrix to do row reduce operations, okay? Use this matrix to do row reduce operations. Now I'm just gonna go really fast here because it's a lot of work. So I'm just gonna jump straight to it. So after you do row reductions from using this matrix, use this matrix, row reduction of that, and the result comes out to be this. And as you can see, this is my x3, this is my x3, and x3 is a free space, so that's where the 1 comes from. And so the answer opposite of that will be positive, opposite of that will be positive, and then this is my free space, so it'll be 1. So all of my x3 value are here. Now I don't want fractions, so multiply that by a 4. So 4 times 1/4 is 1. 4 times 3/4 gives me 3. 4 times 1 gives me this 4. So this is the first basis or vector that belongs to this eigenvalue 3. Repeat that process to the next eigenvalue, which is 2. So instead of using lambda, I put 2 in. Again, only the diagonal get the 2. Add, subtract across, add, subtract across, add, subtract across will gives me this result. Use this matrix to do row reduction. One more time. Use this matrix to do row reducing. So this matrix is rewritten here. Row reduce it, okay? Again, I'm just going to jump to the answer because it's a lot of work. So this is the solution to this after row reducing. And as you can see, this is x3, x3, and this is x3 because it's a free space. I get a 1. So opposite of negative 2/3, positive. Opposite of a negative 1, I get positive. And then since this is a free space, I have 1. Now I don't want fractions, so get rid of this denominator 3. So 3 times 2/3 is just 2. 3 times 1 is 3. 3 times 1 is 3. This is the second base or vector, basis or vector that belongs to this eigenvalue 2. Okay, next, the last eigenvalue is this 1. Again, don't put lambda, put 1 in. So only the diagonal get this 1. Okay, and then just subtract across, subtract, add across, subtract, add across will gives me this. Use this matrix and do row reducing. One more time. Use this matrix, which I have here, row reduce this matrix. For the sake of time and a lot of work, this right here is the solution to this matrix after row reducing. Again, this is the result, the solutions, the solution from this matrix after doing row reducing. And as you can see, this is x3, x3, and also x3. So opposite of -1, positive, opposite of -1, positive. Since this is a free space, so 1. And there's no fraction here, so that makes it easy. So the third basis or vector is this one that is belong to this eigenvalue. One more time. This vector or basis belong to this eigenvalue. This basis or vector belong to this eigenvalue. This vector belongs to this eigenvalue. Now put these three vectors together. That will give me my P. Okay. Again, put this vector and vector and vector, or put all three of these bases right here together to give me my P. So again, the P matrix has all of the bases or vectors that belongs to the eigenvalue. The D matrix is the eigenvalue only. One more time. The P matrix is the basis or vectors of vectors that belongs to the eigenvalue, okay? And the D matrix is the only eigenvalue, okay? Now, for the sake of time, I know this is a lot of work here, so we will assume that this is true and this is also true, because when we check this, it's going to be a lot of work. So I'm just going to jump to the answer and we'll just assume that it is true. Okay, so one more time, make sure every eigenvalue, plug it in, find out that matrix, do row reducing, that comes out to the result. This is the result of this after row reducing, and then label all my terms out for each of the x, and in this case it's just x3. This is my basis or vector that belongs to eigenvalue 3. Same thing with here. Put the 2 in, row reduce this matrix, what I have here. This is exactly what I have here. Row reduce this matrix. This is the results, and it comes out to the be the vector or basis that belongs to eigenvalue 2. Again, row reducing, make sure you remember how to do row reduce. Now there's a lot of work here, so I skip all that and I just go to the result. And the last one, eigenvalue 1, same thing. Do row reduce on this matrix, okay? Row reduce on this matrix. That's what I wrote again over here. And this is the result from, this is the solution from this matrix after row reducing. And this is the vector or basis that belong to this eigenvalue, okay? After that, put this vector together, and it will become the matrix, P. Again, P is the matrix that has all of the all of the vectors or basis that belongs to its eigenvalue. The D matrix is the eigenvalue only. One more time, P is the basis or vectors that belong to the eigenvalues. Matrix D only has the eigenvalue. And for the sake of time and process, we will just assume that this format and the second format is true.